May 1960, Sverdlovsk, Soviet Union. A CIA pilot named Francis Gary Powers sat in the cockpit of his U-2 spy plane at 70,000 feet when a Soviet surface-to-air missile exploded beneath him. The U-2, America's most advanced reconnaissance aircraft, tumbled from the sky. Powers survived and was captured. The incident exposed a crisis that would reshape aviation forever. The Soviets could now shoot down America's highest-flying spy plane. The United States needed something faster, something higher, something that seemed impossible by every standard of aeronautical engineering. In a windowless building in Burbank, California, a 49-year-old engineer named Kelly Johnson read the intelligence reports and made a promise that defied physics. He would build an aircraft that could fly at Mach 3, sustain temperatures hot enough to melt aluminum, and outrun any missile the Soviets could fire. His team had 20 months. Most aviation experts said it couldn't be done. They were wrong. The story begins not with the SR-71, but with a culture of impossibility. The year was 1943, and Lockheed Aircraft Corporation had just received an urgent request from the Army Air Corps. The British had intelligence about a new German jet fighter, the Messerschmitt 262, that could fly 100 miles per hour faster than any Allied aircraft. America needed a jet fighter, and they needed it immediately. The timeline was absurd. Design, build, and fly a prototype in 180 days. Lockheed's chief engineer, Hall Hibbard, gave the project to his best aeronautical engineer, Clarence Leonard Johnson. Everyone called him Kelly, a nickname from childhood. Johnson was 33 years old, brilliant, abrasive, and utterly intolerant of bureaucracy. He assembled a team of 23 engineers and 30 shop mechanics. They worked in a rented circus tent next to the Burbank airport because every proper facility was occupied with war production. The tent reeked of a nearby plastics factory. Someone joked they were working next to a skunk works, a reference to a moonshine operation in the comic strip Lil Abner. The name stuck. Johnson's team worked 7 days a week, often through the night. They had no time for the standard corporate procedures, no endless meetings, no layers of approval. Johnson made decisions instantly. If a design didn't work, they scrapped it and tried something else. If they needed a part that didn't exist, they made it. The Skunk Works team produced the airframe in 143 days, 7 days ahead of schedule. They delivered it to Muroc Army Airfield on November 16, 1943. The first prototype was nicknamed Lulu Bell. It flew on January 8, 1944, with Lockheed test pilot Milo Burcham at the controls. Within 5 minutes, Burcham was back on the ground, spooked by the sensitivity of the controls. Johnson told him the aircraft had a 15-to-1 aileron boost and was naturally sensitive. Maybe he was over-controlling. Burcham tried again, and on his second flight had Lulu Bell up to an unprecedented 490 miles per hour. The XP-80 eventually reached a top speed of 502 miles per hour, making it the first turbojet-powered U.S. aircraft to exceed 500 miles per hour in level flight. The P-80 Shooting Star changed everything, not because it was the fastest or the most advanced, but because it proved something fundamental about what was possible when someone questioned the rules. Johnson had violated every principle of aerospace development. He'd designed an aircraft in weeks, not years. He'd built it in a tent, not a factory. He'd skipped the committees, the reviews, the bureaucratic processes that everyone said were essential. And he'd delivered ahead of schedule. The lesson wasn't lost on the military. When they needed something impossible, they knew where to go. By 1955, at the request of the Central Intelligence Agency, Johnson initiated construction of the airbase at Groom Lake, Nevada, later known as Area 51. This project provided a secret location for flight testing the Lockheed U-2, another aircraft that conventional wisdom said couldn't be built. The U-2 could fly at 70,000 feet, far above the range of Soviet fighters and missiles. For years, it operated with impunity, photographing Soviet military installations, nuclear facilities, and strategic assets. But the U-2, for all its capabilities, had a fatal flaw. It flew high but not fast. On May 1, 1960, Francis Gary Powers took off from a base in Pakistan bound for Norway, with his planned flight path crossing 2,900 miles of Soviet airspace. Near Sverdlovsk in the Ural Mountains, a Soviet SA-2 surface-to-air missile detonated close enough to Powers' aircraft to send it spiraling toward Earth. Powers ejected and parachuted into Soviet territory. The Soviets displayed the wreckage in Moscow like a trophy. Soviet Premier Nikita Khrushchev used the incident to humiliate President Eisenhower on the world stage. The political fallout was catastrophic. A planned summit between Eisenhower and Khrushchev collapsed. The Cold War, briefly thawing, froze solid again. But more important than the diplomacy was the technical reality. Altitude alone wasn't enough anymore. The Soviets had missiles that could reach 70,000 feet. America's intelligence-gathering capability was compromised. The military and CIA needed a replacement for the U-2, but the requirements were staggering. The new aircraft would need to fly higher than the U-2 and faster than any missile. It would need to be nearly invisible to radar. It would need to operate over hostile territory for hours at a time. And it would need to do all of this while carrying cameras and sensors sophisticated enough to photograph Soviet installations from the edge of space. Work on what would become the SR-71 had actually begun in the late 1950s, even before Powers was shot down. Kelly Johnson, always thinking ahead, had started developing designs for the A-12 reconnaissance aircraft under the CIA codename Oxcart. The fundamental requirements were clear: low radar cross-section, high altitude capability, and speed. Extraordinary speed. The aircraft needed to cruise at Mach 3.2, just over 3 times the speed of sound, at altitudes up to 85,000 feet. The problem was heat. At Mach 3, friction with the atmosphere generates temperatures exceeding 1,000 degrees Fahrenheit on the aircraft's leading edges. The cockpit windows would reach 600 degrees. The fuselage would glow red-hot. Aluminum, the standard material for aircraft construction, melts at 1,220 degrees Fahrenheit. Even if it didn't melt, it would weaken structurally long before reaching that temperature. Steel was strong enough to withstand the heat, but it was too heavy. An aircraft made of steel couldn't achieve the performance requirements. There was only one material that could work: titanium. Titanium alloy provided the strength of stainless steel at about half the weight. It could withstand temperatures exceeding 1,000 degrees without losing structural integrity. It was the perfect material for a Mach 3 aircraft. There was just one problem. Actually, there were several problems, but they all related to titanium being one of the most difficult materials to work with in manufacturing. Titanium is extraordinarily reactive. When heated, it absorbs oxygen, nitrogen, and hydrogen from the air, becoming brittle and prone to cracking. This meant that all welding and heat treatment had to be done in inert atmospheres, typically using argon gas. Conventional manufacturing techniques didn't work. New processes had to be invented. New tools had to be designed. Even the rivets had to be titanium, because using steel rivets would create galvanic corrosion that would weaken the structure. The Skunk Works team discovered that cadmium-plated steel tools, standard in aerospace manufacturing, caused titanium to become brittle on contact. They had to design and fabricate new tools made from titanium itself. Drilling titanium required different drill bits, different speeds, different techniques than drilling aluminum. The material would work harden as it was machined, meaning that tools would dull rapidly. Machinists who had spent careers working with aluminum had to learn entirely new skills. But the biggest problem with titanium was more awkward than technical. In the early 1960s, the Soviet Union was the world's largest supplier of titanium. The United States didn't have adequate domestic sources of rutile ore, the raw material for titanium production. To build an aircraft designed to spy on the Soviet Union, Lockheed needed to buy massive quantities of titanium from the Soviet Union. The solution required creativity that had nothing to do with engineering. The CIA set up shell companies and used third-world intermediaries to purchase Soviet titanium without revealing the end user. According to former SR-71 pilot Colonel Rich Graham, the U.S. used bogus operations to acquire the titanium needed to design the SR-71 airframes. One of the fake companies supposedly purchased titanium for manufacturing pizza ovens. The Soviets, unaware they were supplying material for an American spy plane, shipped the ore. Ben Rich, who succeeded Kelly Johnson as director of Skunk Works, later detailed how Titanium Metals Corporation had only limited reserves of the precious alloy, so the CIA conducted a worldwide search. Using third parties and dummy companies, they managed to unobtrusively purchase the base metal from one of the world's leading exporters, the Soviet Union. The Russians never had an inkling of how they were actually contributing to the creation of the airplane being rushed into construction to spy on their homeland. The irony was exquisite. Soviet titanium would be forged into an aircraft designed to photograph Soviet military secrets. The same raw material that the Soviets used for their own submarines and military applications would fly over their territory at 3 times the speed of sound, untouchable by their air defenses. In total, Lockheed would build more than 50 aircraft from the basic design: 13 A-12s for the CIA, 2 M21 variants that carried reconnaissance drones, 3 YF-12 interceptor versions for the Air Force, and 32 SR-71 reconnaissance aircraft. Every single one constructed primarily from Soviet titanium. But sourcing the material was only the beginning of the challenges. Kelly Johnson later said that everything had to be invented for the SR-71. Everything. The statement wasn't hyperbole. Every system on the aircraft pushed beyond existing technology. The engines were a masterpiece of engineering. Pratt & Whitney designed the J-58 turbojet specifically for sustained Mach 3 flight. At low speeds, it operated as a conventional turbojet. But as the aircraft accelerated past Mach 2, bypass tubes would open, routing air around the engine core. At Mach 3.2, about 80% of the thrust came not from the engine itself, but from the inlet spike and bypass system, which essentially turned the engine into a ramjet. The engine had to function efficiently across a speed range from 0 to over 2,000 miles per hour, from sea level to 85,000 feet. No engine had ever been asked to operate across such extremes. The fuel system was equally revolutionary. The aircraft used JP-7, a specialized fuel that was extraordinarily stable at high temperatures. JP-7 was so stable that you could drop a lit match into a bucket of it, and the match would go out. The fuel wouldn't ignite. This was necessary because the fuel tanks were integrated into the aircraft structure, and the fuel itself served as a heat sink, absorbing thermal energy from the airframe. As the aircraft flew at Mach 3, the fuel would heat up to several hundred degrees. Conventional jet fuel would have exploded. Starting the engines required a chemical called triethylborane, which ignites spontaneously on contact with air. Each engine start consumed a small amount of this volatile chemical, and the aircraft carried enough for about 16 starts. If you ran out of triethylborane during a mission, you couldn't restart the engines. Pilots learned to be very careful about engine management. The hydraulic system used fluid that could function at temperatures ranging from -40 degrees Fahrenheit at high altitude to over 600 degrees in the hot sections of the aircraft. The tires were filled with nitrogen instead of air, because regular air would expand too much during the heat buildup of a high-speed landing. The brakes were designed to handle the enormous energy of stopping an aircraft landing at over 180 miles per hour. Even the paint was special. The SR-71's distinctive black color wasn't chosen for aesthetics or stealth. The paint contained microscopic iron ferrite spheres that absorbed radar energy, helping reduce the aircraft's radar cross-section. But more importantly, the black paint helped radiate heat. At Mach 3, every bit of heat dissipation helped. The aircraft was officially painted with iron ball paint, which gave it the nickname Blackbird. The aircraft's shape was based on the earlier A-12 design, refined through extensive wind tunnel testing and later through computational analysis. The design featured a blended wing-body configuration that reduced drag and provided lift across the entire airframe. The twin vertical stabilizers were canted inward for stability at high speeds. The fuselage had a narrow cross-section to minimize wave drag at supersonic speeds. Every surface, every curve, every angle was optimized for performance at Mach 3. But perhaps the most remarkable aspect of the SR-71 was that it was designed to leak. The titanium skin panels were designed to fit loosely at room temperature. During ground operations, the aircraft would drip fuel from the tanks. This wasn't a flaw, it was intentional. At Mach 3, the airframe would heat up and expand, and the panels would seal properly. The aircraft only achieved its designed performance when flying fast enough for the heat to expand the structure. This meant that every SR-71 mission followed the same basic profile. Take off from base, accelerate to cruise speed, and the aircraft would heat up and seal. But the initial fuel load wasn't enough for a full mission. After takeoff, the SR-71 would rendezvous with a tanker aircraft, usually a KC-135Q, and refuel in mid-air. Only then would the aircraft proceed to its mission area. It was an aircraft that only worked properly when flying at 3 times the speed of sound. The first A-12 took flight on April 26, 1962, at Groom Lake. Test pilot Lou Schalk lifted off and immediately experienced control difficulties. The aircraft wobbled dangerously before Schalk managed to bring it down onto a dry lake bed. The problem was traced to the flight control system, which was redesigned. Subsequent test flights were more successful, though the test program revealed dozens of issues that needed correction. By 1964, the A-12 was operational, flying reconnaissance missions over Cuba and later over North Vietnam under the CIA program codenamed Black Shield. But the Air Force wanted its own variant with greater range and the ability to carry a crew of 2. A pilot, and a reconnaissance systems officer to manage the cameras and sensors. This variant became the SR-71. The SR-71 was longer than the A-12 to accommodate additional fuel tanks and a second cockpit. The lengthened fuselage gave the aircraft greater range, crucial for missions that might require hours of flying over hostile territory. The reconnaissance systems officer sat behind the pilot in a separate cockpit with his own instruments and ejection seat. The 2-person crew allowed for better management of the complex reconnaissance systems, while the pilot focused on flying the aircraft and monitoring the engine performance. In 1964, President Lyndon Johnson announced the existence of the SR-71 to the public, though he accidentally referred to it as the SR-71 instead of the correct designation RS-71. Rather than correct the president, the Air Force simply changed the designation to match what he had said. The aircraft entered service with the United States Air Force in January 1966. The operational reality matched the engineering promise. SR-71 pilots and reconnaissance systems officers trained for months before their first operational mission. They had to learn to fly an aircraft that handled differently at Mach 3 than at subsonic speeds. They had to learn to navigate over featureless terrain from 85,000 feet. They had to learn to manage complex systems while wearing pressure suits in case of cabin depressurization. During missions, if a surface-to-air missile was fired at a Blackbird, the pilot's response was simple: accelerate. The standing orders were to push the throttles forward and outrun the threat. At Mach 3.2, the SR-71 was faster than any missile. By the time a missile climbed to 80,000 feet, the SR-71 was already miles away, having accelerated beyond the missile's maximum speed. Over its operational career, more than 4,000 missiles were fired at SR-71s during reconnaissance missions. Not one ever hit. The aircraft's combination of speed, altitude, and small radar cross-section made it effectively invulnerable. Soviet air defense commanders tracked the aircraft on radar, watched it fly over their territory, and could do nothing to stop it. The frustration was palpable in intercepted Soviet communications, as pilots in MiG interceptors tried futilely to climb high enough and fast enough to engage the Blackbird. The SR-71 flew reconnaissance missions over North Vietnam, the Middle East, North Korea, and along the borders of the Soviet Union. It photographed military installations, tracked troop movements, monitored nuclear facilities, and collected electronic intelligence. The cameras and sensors aboard the SR-71 could survey 100,000 square miles of Earth's surface per hour from 80,000 feet. The resolution was sufficient to read license plates from the edge of space, but the operational costs were enormous. Each SR-71 required extensive maintenance after every flight. The engines had to be inspected and often rebuilt. The specialized JP-7 fuel was expensive. The tanker support required for every mission added to the costs. A single operational SR-71 mission could cost hundreds of thousands of dollars. The Air Force operated a fleet of 32 SR-71s, though not all were mission-capable at any given time. By the 1980s, the strategic calculus was changing. Reconnaissance satellites could provide imagery without the political risks of overflights. Satellites didn't violate airspace. They didn't require tanker support. They didn't risk pilot lives. The satellite imagery was often better than what the SR-71 could provide, with modern sensors achieving resolutions measured in inches rather than feet. In 1989, the Air Force announced the retirement of the SR-71 fleet. The official reasons cited were costs and the availability of satellite reconnaissance. But politics played a role as well. The end of the Cold War reduced the urgency of maintaining such an expensive reconnaissance capability. The SR-71s were placed in storage, their operational careers apparently over after just over 2 decades of service. But the retirement didn't last. In 1995, Congress voted to reactivate several SR-71s for operational use. The Air Force, under political pressure, brought 3 aircraft back into service. The reactivation revealed how difficult it was to recreate the operational infrastructure. Many of the specialized technicians had retired. Some of the unique tools and test equipment had been disposed of. The supply chain for parts had been dismantled. Bringing the aircraft back into service cost far more than keeping them flying would have cost. The second operational period was brief. By 1998, the SR-71 was retired again, this time permanently from Air Force service. NASA continued operating 2 SR-71s for research purposes, using them as high-speed test beds for experiments in aerodynamics, propulsion, and atmospheric science. NASA's SR-71 program continued until 1999, when the aircraft flew their final missions. The SR-71 set numerous speed and altitude records throughout its career. In 1976, an SR-71 set the absolute altitude record of 85,069 feet and the absolute speed record of 2,193 miles per hour. Both records still stand for air-breathing manned aircraft. On its final flight on March 6, 1990, an SR-71 flew from Los Angeles to Washington, D.C. in 1 hour, 4 minutes, and 20 seconds, averaging 2,124 miles per hour. The aircraft was flown directly to the Smithsonian's National Air and Space Museum, where it remains on display. In total, 12 of the 32 SR-71 airframes were lost to accidents over the aircraft's operational life. Several were lost to engine failures. Others crashed due to system malfunctions or pilot error. But not a single SR-71 was ever shot down by enemy fire. Despite flying thousands of missions over hostile territory, despite having more than 4,000 missiles fired at them, the Blackbirds returned safely from every combat mission. The legacy of the SR-71 extends far beyond its performance specifications. Kelly Johnson's management philosophy, formalized as Kelly's 14 Rules, became a model for innovation in aerospace and other industries. The rules emphasized small teams, minimal bureaucracy, direct communication, and trust in engineers to solve problems. The success of Skunk Works demonstrated that the traditional approach to aerospace development wasn't the only way, and often wasn't the best way. Johnson played a leading role in the design of over 40 aircraft during his career at Lockheed. Beyond the P-80, U-2, and SR-71, his designs included the F-104 Starfighter, the C-130 Hercules transport, and numerous other aircraft that became icons of aviation. He received the Medal of Freedom in 1964, 2 Collier trophies for aeronautical achievement, and numerous other awards and honors. But Johnson consistently turned down promotions that would have taken him away from engineering. He was offered the position of Lockheed president 3 times and declined each time, preferring to remain at Skunk Works where he could focus on designing aircraft rather than managing corporations. He remained a senior advisor at Skunk Works even after his formal retirement in 1975, consulting on projects until shortly before his death on December 21, 1990. The SR-71 Blackbird remains on display in museums across America. The Smithsonian's National Air and Space Museum in Washington displays the record-setting aircraft that made the final coast-to-coast speed run. The Museum of Flight in Seattle, the Strategic Air Command Museum in Nebraska, the Pima Air and Space Museum in Arizona, and numerous other facilities house Blackbirds. Visitors stand beneath their titanium skin, marveling at aircraft that still look futuristic more than 60 years after the first A-12 flew. What visitors are really looking at is proof of concept. Proof that one engineer, freed from bureaucracy and empowered by necessity, can accomplish what committees say is impossible. Proof that the constraints we accept as immutable are often organizational rather than physical. Proof that impossible often means nobody has figured out how yet. The story of the SR-71 is ultimately about questioning limits. For decades, aviation experts said sustained Mach 3 flight was impossible. The thermal problems were insurmountable. The materials didn't exist. The engineering challenges were too great. The costs were prohibitive. Kelly Johnson heard those objections and built an aircraft that flew at Mach 3.2 for hours at a time, constructed primarily from Soviet titanium purchased through shell companies supposedly buying material for pizza ovens. The parallels to Johnson's earlier work are obvious. With the P-80, experts said you couldn't design and build a jet fighter in 6 months. Johnson did it in less than 5. With the U-2, experts said you couldn't build an aircraft that flew at 70,000 feet. Johnson built one that flew at 72,000 feet in 9 months. With the SR-71, experts said sustained Mach 3 flight was physically impossible. Johnson proved them wrong, and the aircraft remained operational for over 30 years. The pattern is consistent across all of Johnson's achievements. Identify the fundamental requirements, strip away everything unnecessary, assemble a small team of the best people available, give them authority, resources, and protection from bureaucracy. Get out of their way and let them work. Iterate rapidly based on test results. The approach worked regardless of the specific technical challenge because it addressed the real obstacle. Not technical limitations, but organizational and conceptual constraints. The SR-71 flew reconnaissance missions over hostile territory for 3 decades. It photographed Soviet military installations, Vietnamese supply routes, North Korean facilities, Middle Eastern conflicts, and countless other targets. Throughout its nearly 33-year career, counting both operational periods, the Blackbird remained the world's fastest and highest-flying operational manned aircraft. From 80,000 feet, it could survey 100,000 square miles of Earth's surface per hour, with cameras capable of resolving objects less than a foot across. But the SR-71's real contribution was demonstrating that human ingenuity, properly organized and challenged, could overcome obstacles that conventional wisdom deemed insurmountable. The thermal problems that made Mach 3 flight impossible were solved through material science and innovative design. The titanium manufacturing challenges that made the aircraft unbuildable were solved through new processes and techniques. The costs that made the program economically impossible were justified by the strategic value of the intelligence gathered. Today, more than 2 decades after the SR-71's final retirement, no operational manned aircraft has matched its sustained speed. Lockheed Martin has proposed a successor, the SR-72, with a planned first flight that has been repeatedly delayed. Whether that aircraft ever flies or not, the SR-71's records stand as a testament to what one engineer and his team accomplished when they refused to accept that impossible meant impossible. The technological barriers that the SR-71 overcame remain impressive by modern standards. Sustained Mach 3 flight is still extraordinarily difficult. The thermal management challenges haven't gotten easier. The complexity of designing an air-breathing engine that functions efficiently from 0 to over 2,000 miles per hour remains formidable. Modern aircraft designers, with decades of additional knowledge and computational tools that Johnson never had, still struggle with the same fundamental problems. What made the SR-71 possible wasn't superior technology. It was superior organization and a willingness to challenge assumptions. Johnson's Skunk Works operated under principles that violated standard aerospace practice. Small teams instead of large departments, direct communication instead of formal hierarchies, rapid prototyping instead of extensive analysis, authority delegated to working engineers instead of concentrated in management, trust in people to solve problems instead of detailed procedures. These principles worked for the P-80 in 1943. They worked for the U-2 in 1955. They worked for the SR-71 in 1964. They continued working for subsequent Skunk Works projects, including the F-117 stealth fighter in the 1980s. The consistency of success across different technologies, different eras, and different challenges suggests that the principles themselves, not the specific technical solutions, were the real breakthrough. In May 1960, Francis Gary Powers fell from the sky over Sverdlovsk, and America faced a reconnaissance crisis. The Soviets could shoot down spy planes. America needed something faster, something better, something impossible by the standards of contemporary aviation. Kelly Johnson promised to build it. 5 years later, the SR-71 Blackbird was operational, flying higher and faster than any aircraft before or since. The SR-71 didn't just spy on the Soviet Union using Soviet titanium. It proved that the boundaries of what's possible are set not by physics or materials or engineering challenges, but by our willingness to question assumptions and challenge conventional wisdom. It proved that impossible often means nobody has figured out how to do it yet, not that it can't be done. Kelly Johnson stood in windowless buildings across his career, making promises that experts said couldn't be kept. A jet fighter in 180 days, a spy plane that flies above 70,000 feet, an aircraft that sustains Mach 3 for hours. Every time, the experts explained why it was impossible. Every time, Johnson delivered anyway. The SR-71 Blackbird, built from Soviet titanium to spy on the Soviet Union, flying at speeds and altitudes that were impossible until they weren't, remains the ultimate expression of Kelly Johnson's philosophy. Be quick, be quiet, and be on time. Everything had to be invented. Everything was. And that, ultimately, is the legacy that matters most. The legacy isn't just about fast planes or high-altitude reconnaissance, or even about the intelligence value of the missions flown. The legacy is proof that human potential, when unshackled from bureaucracy and empowered by necessity, exceeds the limitations that conventional wisdom imposes. The impossible becomes merely very difficult. Very difficult becomes routine. And routine becomes the foundation for the next impossible challenge. The Blackbird sits in museums now, its missions complete, its records still unbroken. Visitors photograph it, read the informational placards, marvel at its sleek black titanium skin and the brutal elegance of its design. Children press their faces against the barriers, staring up at an aircraft that flew before their parents were born and remains faster than anything flying today. What they're really seeing is evidence that one engineer's refusal to accept impossible as an answer changed aviation forever and proved that the boundaries we accept are boundaries we create. Kelly Johnson didn't just build fast planes, he built proof that impossible is negotiable, that the limits we accept often say more about our assumptions than about physical reality. The SR-71 story resonates because it represents something larger than aviation achievement. It represents the potential of human ingenuity when freed from the constraints of conventional thinking. It represents what becomes possible when someone asks not whether something can be done, but how it can be done. It represents the power of refusing to accept that impossible means impossible. And that lesson, more than any speed record or reconnaissance mission, is the enduring gift of Kelly Johnson and the SR-71 Blackbird. The stars seemed impossibly distant until we decided they weren't. Sustained Mach 3 flight seemed physically impossible until someone proved it wasn't. The next impossible challenge, whatever it might be, awaits someone willing to question whether impossible really means impossible, or just means nobody has figured out how to do it yet.